Hello everyone, thank you for coming to our poster session. Our poster is titled The Drop Tower and Plate Glass, a simple and effective setup for controlled lithic experiments. Controlled experiments play a crucial role in studying the flake formation process to explain variability in the lithic assemblages. They have the advantage of controlling the effect of various knapping parameters individually, and Drop Tower is an effective setup for conducting controlled lithic experiments. Past control experiments have discovered that exterior platform angle and platform depth are the two most important factors in determining flake size and shape. However, more attention needs to be given to investigating the force delivery aspect of knapping. There's no unanimous agreement on the effect of different force delivery variables such as angle of blow on flaking, and the interaction between force delivery and different flake variables is not well understood. And here we will investigate the effect of angle of blow and platform width on various flake attributes using the classic drop tower setup. And by angle of blow, we refer to the angle between the hammer blow and the perpendicular of the platform. This means that if you're hitting right perpendicularly at the platform, you will have a zero angle of blow, and as your hammer blow becomes more oblique, the angle of blow will also increase. The flake formation process is governed by uniformitarian laws of fracture mechanics, and here we will study features of the flake's bulb of percussion in the context of fracture mechanics, and this will allow us to link features of a flake's bulb to the angle of blow. And the drop tower setup can effectively control both the striking force and strike location, also the angle of blow during flake removal, and it is also very cost effective. And the design we adopt here for our experiments is from previous work. It is the drop tower is made of a vertical stand with an adjustable supporting pole, and the hammer is controlled by an electromagnetic switch, and the glass core is clamped in device, and by altering its position, we're able to change the angle of blow for flaking. And the striking force is controlled by the hammer mass and drop height. On the right is how a glass core looks like and how a flake looks like from our experiment. And also we're able to control the platform width by changing the thickness of the plate glass. And here are the preliminary results of our study. On the left graph, it shows that the maximum thickness of a flake relative to its platform depth generally decreases as the angle of blow increases. And this is saying that the maximum thickness, which includes the thickness of a bulb on the flake, will reduce as the hammer blow becomes more oblique. And the graph on the right shows that a general pattern that the flake's bulb length will decrease as the angle of blow increases. And this graph, because from this graph we can see that when using the same hammer, flakes produced with the bigger platform width will have longer bulb length than flakes produced with the smaller platform width. To summarize, we find that features of the flake's bulb of percussion reflect changes in the angle of blow and platform width. Our results will help us better understand hominin knapping strategies from the archaeological record. Our results also show that fracture mechanics can provide some novel insights into understanding how hominins control force delivery variables during knapping. And we argue that control lithic experiments informed by fracture mechanics can provide a robust framework to quantify knapping behaviors in the form of tangible lithic attributes. At last, we would like to acknowledge that our study is funded by the European Research Council's StoneCult project. We would also like to thank our colleagues from the metal and glass workshops at the University of Tübingen for their help in our experimental setup. Thank you very much for your attention.